All right, so I'm recording too. Thank you. Good afternoon, everybody. Good day. Welcome to the Energy Systems Engineering Seminar Series. This is the first talk for the spring semester, and I was really glad we are gotten the ball rolling with a very important presentation. Before we get into the presentation, I want to acknowledge that this lecture series is in honor of Janak Raj, who's a past graduate from Lehigh with a master's degree in mechanics back in 1971. But his impact on me was because we were former classmates at the Indian Institute of Technology in New Delhi. And we graduated, as you can well imagine, many, many years ago, more than a half a century. Indian Institute of Technology then was something in the backwaters. Nobody heard about it, but we had terrific buildings, wonderful professors, and great students. And Janak was one of the stars there. In many ways, he was witty, he was smart, he was brilliant, he was a sportsman, very good athlete. And more than anything else, he was very humble. And that's a characteristic that I really remember him very well by. He went on to get an MBA from Sloan School of Management at MIT, and he turned his career from engineering to banking, and he did very well in that capacity too. We lost Janak 3 years ago. And so it's been pretty sad, and I always wanted to do this. And so we had this opportunity to dedicate this lecture series this semester. To kind of remember or pay homage to Janak, I have invited another former classmate, Ashok Ahuja, who's based in Connecticut. So Gulu, go ahead, the floor is yours.
Well, first of all, I'd like to apologize in advance. I'm not good at speaking in front of a group, so you have to bear with me. So I've written it up and I'm going to read it if you don't mind. So first, thank you, Ramesh, Rudy, for asking me to say a few words about Janak, and thank you everybody else for having me. I'm honored to be here to say a few words about Janak, our dear friend. It's weird, as I heard Ramesh talking, it was almost like he and I had shared notes before. So, you know, we haven't spoken about what we were going to talk about. So a brief introduction of myself. I got my undergraduate degree from IIT Delhi and my master's from the University of Cincinnati. I started my career in software working for EDS, a company founded by Ross Perot, one-time candidate for president of the US. After about a decade in the corporate world, my entrepreneurial desires took over. I've been part of a number of startups in the software field, and along the way have run a technology hedge fund. Ramesh and I started together on our BTech EE at IIT Delhi. So it is the 6th decade of our friendship. It is interesting that all of us started off in engineering, and few are left in the field. Ramesh is in that elite group, having built a career in industry before transitioning to education. Ramesh has been instrumental in keeping our classmates in touch over these many decades since our graduation. I met Janak when we were about 9. We were both in St. Columbus, a school run by the Irish Christian Brothers. After that, we both went on to IIT Delhi, with Janak taking mechanical engineering. Pensive, honest, wise, empathetic, humble, intelligent, well-rounded. A sportsman who also happened to excel at sports. Those are all words I associate with Janak. Interestingly, as a professional investor, many of these qualities are what I seek in leaders of companies in which I invest. Janak was an old soul. This was obvious even as a young kid. one of the few such people I have known. After doing his MS at Lehigh, Janak went on to do his MBA at MIT Sloan School of Management. While the rest of us found whatever job we could to help pay our expenses, Janak was enterprising. He bought used cars, many Benzes, I believe, fixed them and resold them. I, on the other hand, had a job working at a beverage company, earning $2 an hour, loading trucks before I moved on to doing the bookkeeping for them. During this period, Janak was reacquainted with Rita Puri, his soon-to-be wife, someone I had also met many years back in the IIT Delhi days. After graduating, Janak moved on to the banking industry, quickly rising through the ranks to top leadership. Janak, along with a couple of associates from Citigroup, with funding from a private equity firm, bought a Japanese bank out of bankruptcy and built it into a worldwide banking leader. Janak was the CEO of major geographic subsidiaries of this bank. I had the good fortune of meeting Janak's family, father, mother, and two older sisters on a number of occasions while at St. Columbus, and his sister and family in Bombay, now Mumbai, during our IIT days. It was always a very pleasant time. At the meal table, it was interesting to me to see Janak conversing and being treated as one of the adults, something that was unusual in India for us anyway. Janak's father was a judge. From the little exposure I had, I would say that Janak blended the qualities of his parents extremely well. A few personal experiences to share. We were able to get our driver's license at age 16. My father taught me and took me to get my auto license. A separate test was required for scooters and motorcycles. Janak spent most of the day taking me to the testing site and let me use his scooter to take the test. Many years later in college, I asked Janak if I could borrow his scooter to leave the IIT campus. Janak said that as a matter of policy, he did not lend his scooter. I assume Janak figured out that a friendship can be damaged or lost over such things. Janak offered instead to take me wherever I wanted to go and bring me back. These are small examples of Janak's friendship and generosity. Sonia, my late wife, was diagnosed with cancer 3 years back. I called Janak for advice. Rita picked up the phone since Janak was very unwell. Janak asked Rita to let him speak to me, to us. Even at that stage, a couple of weeks before he passed, Janak's concern was for Sonia and me. Janak passed a couple of weeks later. I'm really pleased to have been able to call Janak a lifelong friend. Thank you.
Thank you, Gula. I know we have in the audience Janak's daughter, and his wife was also invited. And so I'll just offer Shreya, if you want to say a few words, and then proceed.
Thank you so much. I think it's going to be a little hard for me to say much. I'll just say this. It's really a huge honor to have you do this for my dad and to hear these wonderful memories. I think you guys have described him to a T. And I feel very honored and proud that he made such lifelong friendships that still endure to this day. Thank you very much for doing this. Really, really appreciate it. And of course, I'll be in touch later, but I know that his time at Lehigh was very, very important to him. He was very happy, and he always used to teach us to, pursue the things that were important to us and that had meaning rather than, financial gain, and that the finances would come, but the road to success was really just following what you wanted to do and being a good person about it. Thank you.
Thank you, Shreya. And thank you, Gulu, for this remembrance. And so we will now continue with the agenda, which was a presentation by Revis James on energy technology and policy. And this will be one of a three-part series. And I think this has so many elements that I'm really happy to share with the audience. Why we need to take a holistic view between technology and policy. I struggle to explain this in class. Technology may be the savior, but more often than not, policy always wins, regardless of how reasonable or unreasonable it is. And so Revis, between now and middle of April, I believe, he's going to let us in on what are some of the issues that one needs to look at for a holistic view of energy technology and policy. Just by way of introduction, Revis is a longtime friend of mine. And we worked together at EPRI, where he was there for about 20 odd years as a director. He then went on to become the vice president of the Nuclear Energy Institute in Washington, DC, as a VP of Policy Planning and Development. And so the scope there included electricity market issues, used nuclear fuel, development of advanced nuclear power technologies, as well as financing and tax issues. I had the good fortune of working with Revis in areas of operations and maintenance, instrumentation and control. And I found them to be so creative and so innovative and always fun to be around and work with. So thank you again, Revis. He also spent 2.5 years in Paris, and he's pretty fluent in French. And leading a joint strategic research and development program between EPRI and Electricité de France. As you all know, EDF is one of the largest operators of nuclear power plants, and they've had a very safe record. In fact, 80% of France's portfolio is nuclear, so it's something that we can learn a lot of lessons from. Revis got his Bachelor of Science degrees in nuclear engineering, electrical engineering, and computer science, as well as a Master of Science degree in nuclear engineering from the University of California at Berkeley. Thank you, Revis. And I'll stop sharing the screen and let you get your. You're muted, Revis.
Let me bring a little content up and then I'll start my presentation. Bear with me a moment. Okay, and let's see here. Okay. All right, let me move to the presentation here. Okay, can I confirm, Ramesh, that you are able to see my screen? Okay,
yes, very good.
Well, first, let me just a couple brief remarks just to set up the presentation. First of all, I would just like to echo, I can just tell from the discussion about Mr. Raj and his career. My working with Ramesh over the years, I'm not surprised with the type of people that you're friends with, Ramesh. It all sounds like what a wonderful group. I really enjoyed our time together working. What I'd like to do here is I'd like to just quickly touch on the overall context here. Some of you may have attended a seminar that I gave in the fall series last year in October, in which I tried to integrate many facets of how policy and technology research come together to address future issues that are very complex and not entirely technical and not entirely economic and not entirely policy driven, but a mixture of all three. I think to do that, I'd like to recap a little bit from that presentation, just a few slides. But even before that, let me just say that I think the overarching issue here, and Ramesh alluded to it a moment ago, is that I think we as technical people, researchers, engineers in practice, we have to find a way to make understanding these problems more accessible to policymakers and other stakeholders who are not technical. The ability to do that is going to translate to achieving a sustainable solution in the power sector. And of course, I'll spend some time defining that a little bit more here. But that overarching priority is the key. And I hope that some of these seminars will inspire a few students to pursue an interest in the intersection between technology development and research and policy making. So with that, let me just move on and talk a little bit about sustainability as we define it. Okay, sustainability obviously is a term which many people typically use, I'd say, in a maybe more environmental context. But in this context, it's the intention here is to communicate the idea that there are obviously strong economic drivers in terms of how electricity is produced and delivered. There are, of course, many complicated technical issues. And then, of course, there are a lot of environmental objectives and issues and constraints that have to be addressed. And in terms of this discussion, sustainability is finding a mix of electric power generation technologies which can successfully address constraints and requirements in all of these areas basically indefinitely. As we can all agree, this is an infrastructure that essentially has an indefinite lifetime, and we have to conceptualize approaches that we can envision being sustainable for the foreseeable future. And so that's, of course, adds a lot of complexity here. If you think about what really makes this an important issue, there are some obvious economic factors and some policy factors. One is, of course, that electricity is basically an essential infrastructure now. It's certainly not something optional as it may have been 100 years ago. It's tremendously valuable to economic growth because it is a fungible energy source. Electricity can be used for many different applications, and as simple as that idea is, it's profound. And so enabling the growth of electricity use and production is a hugely enabling capability for so many other facets of human life, even in the developed world as well as in the developing world. Obviously, with greenhouse gas emissions, the ability to decarbonize electricity is going to be a major tool in how we address greenhouse gas emissions and mitigation to the extent we're able to achieve agreement in the policy space. So looking at sustainability, you have to think about a holistic perspective, all these different facets, economic, environmental, and technological, in order to achieve that. And that makes it a very critical priority. And the place that you really have to start is with the production of electricity when you're asking that question. There are, of course, this applies to delivery of electricity and consumption of electricity, and those areas contain many interesting problems. But I think here today, I'm going to look at the generation part of it, since that's the foundation for all the downstream aspects. Another aspect of this situation that I wanted to recap from our last October that's very important to recognize is how many different stakeholders are involved in the power sector. Obviously, there are all of us as individual consumers, businesses and industries as well, but there are a lot of other players, business people who are making money, policymakers who have different objectives, whether it's not only environmental concerns, but employment and economic growth. And overlaid on top of that is the introduction of markets into the electric sector over the last, now I guess it's been 30 years or so. And what has happened essentially is the development of generation technologies and the selection of the mix of technologies which provide electricity in the United States has happened somewhat organically as a sort of a resultant vector from all these different forces acting on it. And you can sort of see that if you look, say, just this is a diagram that Ramesh contributed to the seminar last October. But it just demonstrates how these different stakeholders interact. And interestingly, the retail consumer is not even on this chart. And that's, of course, a whole nother constituency. But it's complicated. Information, requirements, money is exchanged between many different groups. And so figuring out a way to achieve sustainability while meeting the needs of the different stakeholders is very complicated. And so I'm introducing this idea simply to set the table for why it's worth tackling a complicated analysis problem and tackling the communications challenges that go with making the insights from those analyses available to policymakers. And we will get into that with some specific examples here as we move forward. Okay, so a big tool that has played a very important role in achieving this goal of addressing this complex analysis and creating a framework in which all the stakeholders can communicate and debate and reach decisions is energy economic modeling. And that's a very broad area. There are a lot of different types of energy economic models. Many of you probably may be familiar with some of them. In particular, what I wanted to touch on here is that you need the capability to create observability around assumptions and constraints that have to be addressed in order to achieve the sustainability I've been talking about. A very valuable tool of doing that are these computable general equilibrium models. This is a class of energy economic model which essentially looks forward in time based on various assumptions in economic and policy constraints, and allows one to explore sensitivities to different assumptions about the availability or cost of technology, or about the introduction of different policies and so on. Combined with that is a family of models called integrated assessment models, which are designed to tie both technological and economic and other types of constraints together into a single analysis. And there are models which do both. They apply computable general equilibrium approaches to integrated assessment. And these models are very effective. And I'm going to go into an example here, I think, to illustrate that. I think it'll be very interesting for everyone. They are still principally least cost optimization models. So they look at the cost of producing electricity over time and seek to achieve an optimum over a period of time, whatever period of time you set as a modeling objective. Typically, for the type of analyses for these large, far-reaching problems associated with the power sector, the time horizons are often many decades or even hundreds of years in order to explore the long-term implications of different technology decisions. Now, of course, least cost is only one aspect of sustainability, as we were talking about earlier. Overlaid on top of that, one has to consider the capabilities of different technologies, not just in terms of performance, but in terms of lifetime and maintenance and replacement and so on. Also, the way in which electricity is consumed, how those consumption patterns might change, has to be factored in. Really, what these models do is they don't predict, but they enable one to explore different scenarios and perform sensitivity analysis. You can ask questions about fuel costs, you can ask questions about new policies. And as I was saying earlier, the result of that is a complicated framework, admittedly, but very useful framework in which one can look objectively and quantitatively at different assumptions underlying that affect different decisions that may be made or being considered. Historically, utility companies have done that somewhat intrinsically through planning, but a generation technology planning that they do. But this is not really an integrated process, and often some of these non-cost factors are not quantified. And so we'll come back to those topics here a little bit. I think it's important to understand in thinking about this type of analysis, before I get into an example here, is recognizing some pretty unique aspects of the analysis approach that are challenging. And one, of course, as I've been referring to, is really long time frames. This is nuclear plants, coal plants typically have a lifetime on the order of 60 to 100 years. And there's a lot of work in the nuclear sector working to establish a basis for longer lifetimes. And that's been successful now for several decades. And so that trend will continue. Natural gas plants and natural gas combined cycle plants, though initially envisioned with, say, a couple of decade lifetimes, there's been a strong effort to increase their lifetimes as those plants have taken on more of a base load role. By that, I mean, they've taken on a role of generating electricity on a long-term consistent basis rather than simply producing power on demand during short periods of high demand. And that's created demand for, or a desire to have longer lifetimes for those assets. Wind turbines and solar panels, we don't have a lot of operating experience to have a thorough understanding of long-term lifetime performance issues, but 20 plus years for sure is a reasonable framework in which to view these assets. So the timeframes are long, and analysis which enables you to look at the consequences of decisions and assumptions over those timeframes is essential. That's not unique. We have transportation infrastructures, we have water management, we have other infrastructures that have very, very long lifetimes, and we face similar economic and policy-making decisions in those areas. So this is not a unique problem, but the power sector, I think, is still evolving a little bit in the sense that with the introduction of markets, it's viewed somewhat like a commodity. This is something, can you find a way to produce produce energy at the lowest cost, instantaneously at this moment? And the longer term timeframes have been left to the domain of the organizations which manage asset development, namely the utilities. And I think it's been emergent partly as a result of concerns about climate change and some other environmental concerns that perhaps a more integrated and holistic view of the strategy for the power sector and generation in particular is needed. The other factor, of course, is that there's some very different patterns of how energy is consumed and used in the major consumption sectors. The industrial sector, heavy industry, large manufacturing facilities, commercial sector. So, all of your middle-sized facilities, for example, data farms, and residential sectors are different in terms of the pattern of usage and how that pattern is just changing with new technology. And all of those different groups have to be incorporated into these analyses. And then, of course, the other factor is referring to the stakeholders that I described earlier. There are a lot of competing priorities. What is profitable and desirable for, say, an investor in a wind farm can very often be different than what a power company who's deciding to invest in nuclear and natural gas combined cycle would want. And so there are, of course, many of you are probably familiar, there are policy mandates in some aspects in the power sector that require certain use of renewable generation, for example, or introduce energy efficiency programs, and those have to be taken into consideration when looking at the generation portfolio in the long term. And I've kind of listed here a few of the stakeholders here just to give an idea of that. Another part that illustrates the complexity of this is this last bullet I have on the slide about markets. That is obviously a very complex subject and would merit many presentations of its own, so I can't do justice to that, but I can just briefly allude to this. Essentially, we have markets where we've developed a way to price electricity on an instantaneous basis, and those prices nominally drive wholesale power availability to retail providers who then provide power to consumers. However, as we see other issues arise, for example, reliability and availability issues when we have weather events, or a desire to achieve environmental goals and therefore a desire to increase the generation share for certain assets, there have been additional requirements introduced into markets which address those other goals, but create added complexity in the marketplace as a result. So markets have become somewhat complex in order to nominally preserve economic efficiency while achieving other goals. And so reflecting the character of those markets in any analysis, which is designed to look at the longer term future of the power sector, is complicated as well. So these are all pretty substantial challenges in analysis and modeling, and yet there's some avenues for doing it. So what I want to do here, there'll be another seminar later that will go into this topic in more depth, but I thought it might be useful just to recognize that there are, just to coin a phrase, there's no such thing as a free lunch. All the technologies that exist provide some real assets and strengths and have some liabilities. This diagram was developed by EPRI back about 10 years ago. It's sort of the circles here illustrate where technology has a strength or weakness. The yellow is weaker, green is stronger. The vertical column there are a variety of different aspects, cost, resource requirements, emissions, impacts, availability, and operational flexibility. And the vertical columns going down there are the different aspects: coal, natural gas, nuclear, hydro, winds, biomass, and so on. And it is important, really. You can digest this chart later, but what's important is you can see a pattern here. There are a healthy distribution of strong positive characteristics across many technologies for addressing many issues, and there are also some liabilities. And so there really is not a silver bullet. The phrase that people like to use, many of you may have heard of this, is they refer to the concept of silver buckshot. We need an assortment of different tools in the portfolio to address many different requirements that we have. And the art is finding the right combination of technologies such that things will evolve over time to continue to be optimal in addressing all of these different requirements. So this chart maybe gives you a little bit of a vision of that diversity and choices that have to be made. So what I'd like to do now is I'd like to dive into an example. Now, there are a lot of different energy economic analyses out there. A lot of you may be familiar, of course, with the well-known World Energy Outlook, which is annually prepared by the International Energy Agency. The other big one is the Annual Energy Outlook, prepared annually by the U.S. Department of Energy's Energy Information Agency. And those analyses use many of the same concepts I've discussed here. They have somewhat different objectives in terms of understanding. I'd say both of those analyses are meant to be a little more geared towards giving you a window towards, based on current trends and what we know about current trends in fuel and technology and policy, where the power sectors or energy sector is likely headed. The World Energy Outlook that is prepared by the International Energy Agency looks at energy as a whole, doesn't just look at electricity. The Annual Energy Outlook is also looks at energy as a whole, although there's maybe a little bit of a heavier emphasis on electricity in that analysis. However, what these studies typically don't do as much of is looking at scenario and scenario analysis sensitivity studies that are designed to explore in more depth some of the implications of different technology choices that could be made, either on the basis of economics or on the basis of technology development and research. And so other researchers, among them EPRI, have tackled that particular facet of analysis. And this particular example that I've brought up here, this is just the cover page of the report. I've included the citation. Many of you, if you want to, this is a public domain report. You can go download it and look at it in a lot of depth. It was done about 7 or 8 years ago, or 6 or 7 years ago. And what it did is it was intended to look at a couple of 3 questions here. It was intended to look at, since natural gas and fracking were introducing more natural gas supply at a low price, the desire was to look at how the power sector might achieve these various constraints if we continue to have low power gas for a longer period of time, or if we see higher price gas later in time. And by later, I mean decades. On top of that, the study attempted to look at 2 other important variables. One was the introduction and growing generation share of renewable energy, wind and solar primarily. And that's important, not only from an environmental standpoint or an economic standpoint, but because those assets are not dispatchable. They cannot be turned on and off when desired. So they create some interesting operational challenges. And the goal here was to investigate that. And then a final variable was the degree to which we might have to expand the interconnection between different regions of the country from a transmission perspective. As one large connected system, the connectivity of the different regions in the country has a very big impact on how individual regions of the country address power availability and supply, as well as policies. And so the goal was to investigate a little bit about where the trends might be going in terms of need for a change in transmission connectivity. So my point in selecting this particular example is that these are somewhat disparate problems. You know, looking at a particular fuel gas and its price sensitivity, looking at the transmission network and what impacts the ability to expand it or not expand it could have, and looking at the impact of introducing renewable energy with the characteristic of non-dispatchability. These are all somewhat different facets. And the key here is this analysis tried to holistically understand some of these effects together. And to do that, some of this type of modeling I've referred to had to be used. And so I felt this would be a good example to understand what the utility is of developing these integrated models, which look at these different variables, because you can see the sensitivity studies that are needed need to not only look within one domain, like say fuel price variability and how different generation technologies have larger or smaller shares, but also look at how a change in a variable like fuel price could have an impact in a different area like transmission needs. So I think we should go into this just a little bit, and I think you'll see some interesting things. And I expect the questions and answers will be interesting as a result of that. Let me just briefly, I don't want to bore everyone with a dissertation on energy economic models, and I'm certainly not an expert. I'm an engineer. I'm not an energy economist, which is the type of individual who develops these models. But I want a few characteristics are important to understand. So typically what these models do, well, this particular model, let's refer to this one. This is called US Regen. Regen is an acronym which refers to let's see here, what's the title of it? The U.S. Regional Energy Greenhouse Gas and Economics Model. That's the title of this particular model. It's been around now for, I think, over 10 years, maybe 15 years or so after we developed it. What it does is it looks at the problem of capacity expansion. As energy demand grows, how much more electricity do you need? And therefore, how do you add capacity in different parts of the country to meet that need? And of course, inherent in that is choice of technologies. What technologies are used to meet that capacity growth? That's part of it. Another part is to recognize that the policy issues and investment requirements influence the generation technology choices that you make, and different technologies like, for example, the dispatchability, the capability of operating flexibly, meaning increasing or decreasing output, versus technologies that aren't dispatchable. Those factors have to be accounted for. Looking at the interconnection between regions, sometimes a region can import energy rather than build assets within a region. So understanding how energy can be exchanged between regions is important. And then you want to have this look ahead in time, being able to look ahead at how, if these things are done now and we apply requirements over time, how might the generation technology mix change in response to those constraints over time. And so this look ahead capability that you get with computable general equilibrium models is another important capability. So those are the sort of some key features of the US regen model. And that model was used in this particular study to investigate these questions of natural gas price variability, need for interregional transmission, and the impact of introducing more non-dispatchable assets into the generation mix. And we'll get into that in more detail. So here is an example of one of the outputs that you get. This particular chart, I'm not worried about real detailed features of these charts. You can all look at these things more closely later. I think I wanted to illustrate some contrast. That's why I've taken the liberty of packing a lot of information on some of these charts. What this is, this 4-panel chart shows how the generation mix, which technologies are producing electricity over time for the entire US, changes over a 40-year period or so between 2010 and 2050, based on a sort of a reference scenario with current policies and fuel prices, then in scenarios where natural gas prices are high or relatively low, and then in a scenario where gas prices are high and there's no expansion of interregional transmission. And there's a lot of fine structure in these charts, but what's interesting is that the probably most important thing is if you look at the lower left panel and the upper right panel, the high gas scenario in the lower left and the low gas panel in the upper right. Obviously, the orange region is the region which is natural gas production, and it's much larger in the low gas price, as you'd expect. That obviously isn't particularly insightful per se, but what is important to recognize is that the amount of change in the generation share in those two cases is quite large. And that suggests that decisions about the future portfolio where natural gas, say, would play a larger role means that one is creating a larger exposure to price volatility. You will see a much greater sensitivity of electricity production if the larger gas plays a role in the portfolio. So that is a factor in considering how to construct a portfolio and develop a portfolio over time. And so that's understanding how big that sensitivity is an important input. That's the key. Another interesting sort of subtlety, and Ramesh, I'll need your help here. I'm increasing the size of the screen, so we're zooming in on just 2 of the panels. Can that be seen?
That can be, and people have a way of adjusting their own screen,
Okay, well,
so it's really very dynamic. You can do a lot of cool things.
Okay, I'm gonna take the liberty of expanding here, and I'm just gonna look.
I can see it.
Okay, good. So what I would like to do is point out a few features between this high gas scenario and this high gas scenario without transmission expansion on the right. At face value, if you glance at them, they may not look all that different. But this is where these analyses are interesting and powerful. There's actually a lot of information embedded in this. So one thing I will point out is, if you look at the orange band, which represents natural gas, it doesn't appear at face value to be all that different, although it is slightly larger on the new transmission side. And I say slightly, numerically speaking, actually, it's not slight. The difference is somewhat significant. And the reason for that is that without transmission expansion between regions, regions, it's more optimal then becomes optimal to make more investments within each region to develop in region-specific assets. Whereas in the left panel, interregional exchange of energy allows different regions to avoid having to invest in development of assets. So that's a little insight. Another one that's interesting is that with the no transition expansion, the shift in technology that occurs is a shrinkage of the green region, which is I believe that's the wind. Go back here and check that. It's the wind, yes. So that's an interesting insight. One can ask the question, why does wind have a characteristic that makes it a little more vulnerable with lack of transmission? And the answer here is that since wind is not dispatchable, when there is no transmission expansion capability and energy demand gradually grows, and keep in mind here, I should make a caveat here. Although many of us have seen reports and talks about how electricity demand has not grown much in recent years, over multi-decadal periods or 100 years plus, energy usage is essentially proportional to population growth, and we are seeing growth in population. So in the longer run, energy demand growth is a factor in these analyses. So with that caveat, let me move back to the wind. What's interesting about the lack of dispatchability of wind means that in a no transmission expansion scenario, as shown on the right-hand panel here, it means that the model will prefer to expand other dispatchable assets in order to be able to meet the demand during the day and the seasons that is typical of power consumption. If there was transmission capability, such as in the left-hand panel, then more wind is more desirable, because wind's positive characteristics, no emissions, no fuel cost, can become more valuable, because the lack of dispatchability is less of a liability, given that one can import power from other regions and expand transmission if needed. So I wanted to briefly go down this little path just to illustrate how there's a lot of information embedded in these scenarios that one can extract. And then with each of these sort of discussions, one can say, okay, does that make sense? Do we want to do that? Or if the result isn't what one expects, are the assumptions we're making about this technology, or are the way we're characterizing technology in the analysis accurate? And this leads to some really healthy development of very robust analysis. And again, as I said earlier, in developing these studies, you can create clear observability around these assumptions, which enable you to have a discussion with other stakeholders, even people who are not involved in the modeling, but are interested in the results. So this is just one facet. Another facet.
A question, if you're able to answer.
Of course. Go ahead.
What do you mean by dispatchable? You said like wind is not very dispatchable. What does that mean?
Dispatchability means that, for example, with a natural gas plant or a nuclear plant or a coal plant, when the system increases demand, like say, for example, at peak times in the Southwest on summer days when air conditioning is going on, power companies can, tell the power plant to produce more energy. But with a wind or a solar farm, you can't do that. You have to take the energy when it's available, or if it's over generating at a time you don't need the energy, you don't necessarily use all the energy. Now there's a side issue. So fundamentally, the concept of dispatchability is an asset where you can increase or decrease output on demand. That's the definition of it. As it relates to renewables in particular, obviously a very important research area is developing lower and lower cost storage, so that renewables can simply generate whenever they want, that energy can be stored, and then it can be dispatched when needed. That capability, while it does exist in certain areas and in certain facilities, has not yet reached a large scale, because it hasn't yet become economical enough to do that on a large scale. That is a very robust area of research, and I'm sure that will continue to develop. But for the moment, dispatchability is pretty much the assets where you can increase or decrease output based on demand, whereas with non-dispatchable assets, mainly the renewables, you have to take the power when it's available or not use it if it's not needed. Does that help?
Yeah, that
Nick,
helps. Thank you.
Yeah, Nick, we'll cover this in the generation course in the fall. So,
Okay, is it okay if I move on, Ramesh?
yeah, please.
Okay, so here's another facet of this type of analysis that I wanted to get into. And this has to do with the interregional transfer of energy via the transmission network. Okay, so now this picture you're looking at of the United States, these sort of separated areas are the way in which the energy model has divided the transmission regions of the country. I mean, there are a lot of layers of that. I mean, there are actually 4 major, what they call interconnections in the United States. Texas is one, and there's the Eastern Western Interconnect, and as one other one, I think. And then there are, at a much lower level, many different what they call control areas. From a modeling perspective, this particular representation of the transmission network makes sense when you consider the topology of the network. And a study attempted to look at the energy exchange between these regions in different scenarios. And what was really interesting about the study was that with the level of renewable deployment and the level of energy demand growth over the multiple decades timeframe of the study, the expected increase in transition that would be needed, assuming it's possible, if you make the assumption that transition will be expanded if needed to create an optimal production of electricity, so you make that assumption, the level of increase in transition would be pretty substantial. The sort of, oh gosh, I hope this is distinguishable here. There are some 2 red areas here, but yeah, I guess okay, so the what looks like kind of a red area on the screen, Mountain North, Mountain South, Texas, and Northeast Central, those areas in a scenario where you allow transition to expand at a certain cost, there's some assumptions in the analysis, transmission capacity in those areas would have to increase to 5 times what it is now. That means the capacity to move energy between those regions and other regions, that's very large. Though for those of you familiar with transmission networks and the cost, that's huge. The sort of yellow-orange regions, Northwest Central, Southwest Central, Southeast Central, and Florida, though in this particular scenario, those areas would see a 2 to 3 times increase in transmission capacity versus the 2010 levels. And then the lighter colored areas that are sort of yellow, Pacific, New York, Mid-Atlantic, and South Atlantic are 2 times 2010 values. What is interesting about this simply is that, again, it's not important to focus necessarily on the magnitude of the results, but to understand that there's clearly a high sensitivity to the development of the generation portfolio over multiple decades, given other constraints, policy constraints, given fuel prices, given population growth, that suggests that if transmission network is allowed to expand, it would be substantial. And of course, I can assure you that those investments were not being made to expand the transmission network to these levels at that time. And I don't believe that has been, since that time, that kind of investment has been made. So this suggests another sensitivity. And of course, the natural question is, well, if we can't or won't expand the transmission network, then what else can we do so we don't need to have those types of expansions? And that, of course, leads to questions about development of more generation capacity within regions, or energy efficiency programs, or combinations of different strategies to reduce the need to be able to move energy between regions. Recognizing that fact, recognizing how important it is, how the magnitude of it creates visibility around that issue. And that's valuable information, particularly, for example, if you're talking about policy that relates to mandating, say, renewable usage in an area. So this is another dimension of this kind of analysis that is useful in creating this framework that I was discussing back in October about making holistic decisions about the generation portfolio going in the future. So there is, let's see if I can move this on. There is another factor here that I want to get into, and this is regrettably maybe the most complex of all, but this is I know it's a very impressive or confusing chart, but I think it can be broken down. So another question is, so what about the physical requirements on the generation assets we have? As we move forward in time and we meet our policy goals, we meet demand, we obviously want to produce electricity at low cost. We want to meet existing regulations as it relates to emissions or safety and so on. Can the generation mix that we have of power plants today, 10 years, 30 years from now, can they meet all those requirements within the performance envelope physically of those assets? For example, a nuclear power plant can increase and decrease output, but can't do it really instantaneously. With 3-day notice, a nuclear power plant might be able, most plants could probably increase or decrease output by 10 to 20% perhaps, but it takes a little time and needs some advance notice. Alternatively, a natural gas turbine, not a combined cycle, just a natural gas turbine, is like a jet engine. It can increase and decrease output pretty rapidly, which is why a lot of those assets exist for peaking purposes during periods of time when we have rapid changes in energy demand. So this part of the study was designed to ask the question, how does the demand for operational flexibility, decreasing output on short timeframes, change as a function of different scenarios? So this particular chart here is just an example. It's not a particular scenario. I just want to show you how this chart is organized, and I'm going to show you some results. The words here on the left are a list of the regions in the map. So those, let me go back to the previous slide. Each of these regions is a line, horizontal line in this chart. Okay, and then the box, the vertical columns numbered 1 through 52 are 1 week per year. So the 52 weeks in a given year. Okay. And then the colors in the box, each little box. So for example, let me just take the very upper left-hand most corner. New England is the first row, and week number 1, January. The box is kind of a darker reddish color, okay? So what that means is that when you look at a dispatch of units at that time of year for that region, based on knowledge of energy demand in that region, typical weather patterns and so on, as time goes forward, the ability of assets in that region to increase or decrease output on an hour-to-hour basis is going to have to be significant. And you can see the color scale on the bottom here. The closer you get to red, more flexibility is needed. The more to green, less is needed. And the blue boxes are where an extraordinary level of operational flexibility would be needed. And now the report goes into detail defining what exact are the criteria for establishing these colors. There's not enough time here to go through that, but the key idea here is to recognize that you can explore, with these types of models, you can explore the implications of decisions about technologies and about economic and policy assumptions on the operational impact on assets. And you can explore that through a part of the model that looks at how assets are dispatched. Because dispatch of assets happens can happen on an hourly basis, based on how energy demand changes day to day and season to season. And so what I want to show you here is an example that we did looking at some scenarios. We made this type of a chart, but for different scenarios: low gas price, high gas price, the ability to expand transmission or not expand transmission, and so on. So what I have done here is we put this type of chart in. And again, the content of each of these boxes in the report, every one of these individual charts is individually presented and discussed. This is meant to show contrast. That's why this integration. So what you are seeing here is on each row is one of the scenarios that I was showing earlier when I was showing how the generation mix changes over 40 years. The reference case, nominal assumptions about technology capabilities, relatively everything stays kind of the way it is today. The low gas price case, where gas prices tend to go low and stay low over time. High gas prices, they rise and become higher over time. And then a case where the gas prices rise, but transition expansion between regions essentially doesn't happen, can't happen. And then we've looked at specific timeframes, 10-year, 2015 to 25, and then a longer time interval between 2025 and 50. Okay, and then the reason you see these two groups, you see a group entitled US Region Detail Region Texas, and then you see this other group entitled US Region Detail Region Northwest Central. What you do in this type of analysis, and this will come to this touches on an area where we need more development, more capability, but what you do is when you do these models, you look at a particular region, say Texas, and you say, okay, I'm going to model hour by hour the dispatch of every unit in that region. And then I'm going to make broader assumptions about how dispatch is done in the other regions, because I don't have the computational power to do the same thing for all the regions simultaneously. The right-hand group, that was done, except Northwest Central was the region. And there are technical reasons why those two regions were chosen for detailed modeling of unit dispatch. But what is really important in this chart is look at how the colors, the charts seem to have a lot more red and blue in them, are the charts where more operational flexibility is needed by 2050. And you can see, first, one thing you can see in the chart is no matter which scenario you look at, as you move from left to right in either the Texas grouping or the Northwest Central grouping, generally more red appears in the charts. And so that insight is operational flexibility is an important issue almost no matter what the scenario. And subsequent to this research work that was done some years ago, more research was done to investigate other scenarios, and this conclusion was reinforced. Another aspect is you can see, obviously, there are certain charts that have a lot more red. Like, for example, if you look in 2050 on the high gas, no transmission scenario for where the detailed dispatch modeling was done for Texas, there's a lot of red in that chart. That's the kind of at the bottom there in the Texas section. Another interesting thing, so if gas prices were to say due to demand go high, for example, let me go off on another tangent for a moment. Natural gas, for most of the history, the bulk of natural gas in the United States has been used for non-power production purposes. It is only really in the last 10 to 20 years that the amount of natural gas used for power production has risen to a level where it's competitive with and is surpassing what we're using for non-gas purposes. So historically, the sensitivity of natural gas prices from the perspective of electricity production was not as much of a concern because natural gas was not a dominant fuel in the power sector, but it is a very important fuel now. So the sector sensitivity to any gas price changes is more important, and that's obviously an important consideration in terms of future planning of generation portfolios in different parts of the country. Therefore, understanding that suggests that anticipating the need for more operational flexibility is a secondary consequence of that. If you look at the right-hand grouping of panels, and you see in the right column under 2050 for the Northwest Central region where detailed unit commitment was modeled, you see a lot of blue. You can see it in all the charts, particularly as you go downward towards the high gas price and high gas price, no transmission scenarios. Those blue areas are weeks in the year where in particular regions, there will be a tremendous amount of stress on the assets from a standpoint of having to increase and decrease output rapidly within hour periods. The fact that there are so many of those instances is troubling. And that raises questions about what can be done to mitigate that. And I can simply tell you, and this is something that I don't have, we can't go through this today because it's a different area, but a result of this study and some other studies like it that were done was the creation of an entire new research program at EPRI that was focused on something on operational flexibility. As a result of this work, the feeling was we needed to start understanding better exactly what happens to natural gas combined cycles, or what happens to nuclear plants, or what happens to coal plants when we start to flex the output more frequently and over wider ranges than historically has been done. And that program is now, mature, and a tremendous amount of work exists now to develop special operational practices to provide the flexibility needed, but at the same time try to mitigate some of the damage that occurs to the equipment as a result. For example, heat recovery steam generators and natural gas combined cycle plants. So this is another example where this kind of analysis, it's detailed and complex, but when you're able to dive into this analysis, you can recognize and anticipate issues which, if not addressed, might prevent or constrain optionality for policymakers in the future, or for investors, like say a utility company looking to expand capacity later. So this is another facet I thought was important to discuss because it kind of reveals the connection between technical operational issues and very broad economic and policy assumptions that are the inputs to forming constraints that make up this type of analysis. And that connection between those two kind of domains is a really key connection that's important to understand. It's important for engineers and for economists and people interested in public policy to get together and connected on, because it's very difficult to separately look at decisions in any of those domains without tying into the others. And my whole goal here today was to get a message across that integrated analysis, which allows the connection of those domains, is very, very important. Let me go on to one other facet of the Well, it's a summarization, I would say, of this very complex chart I've just shown you. This is basically kind of distilling down the need for added operational flexibility by region from a kind of a color coding scheme. This chart, drawn from this report that was done back in 2015, illustrates that. And so the orange areas are expected, we would expect it to see significant challenge. It's a qualitative statement, but it's based on some quantitative criteria that are described in the report. So these orange regions would see significant challenges in terms of the level of operational flexibility their assets would need to provide. Texas would be very, very challenged, and I'll comment on that in a moment. And some of the regions, the gray regions, mainly due to their high degree of interconnection, would be less challenged. And California, Pacific, Florida, sort of I would call the edge regions of the country that are less interconnected simply because they're on the edge of the country, have some challenges in terms of operational flexibility. California has fewer and fewer generation assets in state, so there's maybe not as much of a challenge as there would be otherwise. Texas is red simply because, as those of you familiar with the transmission network know, Texas is comparatively less connected to the rest of the country. And so whatever operational flexibility needs it has or would have in future scenarios have to be delivered by internal assets, pretty much. Therefore, the challenge for those assets is quite great. In the other regions that have a degree of challenge, but maybe not as much as Texas, they have one strategy for addressing operational flexibility is not to flex your own assets, but to simply import power from a neighboring region. And to the degree that's possible, you can mitigate the operational flexibility challenges for your own assets. That interregional interdependency or lack thereof is another really interesting and valuable insight you can gain from this kind of analysis. Okay, so I've bombarded you with a lot of complexity. I'm certain there are going to be some questions. So let me just wrap up here with a couple of conclusions. First, I like to always point out, given that we're talking as fellow researchers, what are the research directions that you can see just from what's been done so far here? And I focus kind of on modeling here again because it's such a powerful tool. Well, first of all, as those of you who may have picked up from that complex mosaic slide, this one right here. At the time this analysis was done, the ability to do detailed unit commitment modeling, and what I mean by that is, unit commitment means a model that says power plant A will be dispatched on an hour-by-hour basis at 100%, 90%, hour by hour, you actually model what the level of output need from that individual unit is, and you do that for every individual generation asset in a given region. That's obviously a very detailed, complex analysis, computation intensive. What's needed is to integrate that type of modeling completely with these integrated assessment and computable generation equilibrium models so that we can have a fuller view of how these different regions are interdependent and how operational flexibility can be met through different strategies, whether it's intrinsic to the region or in between regions. Another facet, which is very important, but less addressed in this analysis to date, is fuel availability constraints. For example, just recently now this year, but also a few years ago, we've had these events where extreme cold weather reaching the southern part of the United States, like Texas, has negative impacts on gas supply availability for technical reasons and also for competition reasons between power production and for non-power uses. And that leads to unit availability issues. That modeling that and understanding that, in addition to the intrinsic technical limitations of assets, is very important. So that's another area valuable. Many different models exist out there. This US regen model I provided is described as just one of them. There are other groups, consortia of different universities. Most of these groups collaborate a lot, so EPRI collaborates with a lot of these groups. But integrating results from different analyses, which are generally, some of them are stronger, say in the commitment area, some of them may be stronger in terms of how markets are modeled, some may be stronger more in terms of how the transmission network is represented. Integrating results and doing meta-analysis, I think, could be very valuable and could yield some additional insights. Another area that is very important, and I think particularly for this group, this audience, since we're talking here as engineers, is developing approaches, defining what scenarios are valuable, what assumptions require sensitivity studies. Those types of decisions, I was a participant in this type of work for a decade or so. Those types of decisions are often as much the domain of the engineers and people deeply familiar with the technical characteristics of the power sector as they are the domain of the modelers and economists. Those guys depend on the engineering community to understand what's important to look at. Like, for example, I referred to the operational flexibility here issue a moment ago. At the time these analyses were first being done, if you go back maybe 10 plus years ago, the limitations of different assets to increase and decrease output in response to whatever was needed was much less recognized in these models. And as a result, you had model results where assumptions were simply made that whatever level of output was needed, however frequently those changes were needed, that was possible. And it was only then subsequent to that that the engineering community, started to introduce, hey, well, you can't just turn up a power plant or down a power plant without limitation. There are technical reasons why you can't do that, for safety reasons or for cost and reliability reasons. And so that's an example where the engineering community needs to tie in with the modeling community to develop more sophistication and more detail in what types of scenarios and sensitivity studies are needed. So this kind of goes to the concept, what does optimal really mean in terms of a sustainable generation portfolio? Optimal clearly means something that meets a lot of detailed, complex operational needs while meeting all of those economic and policy constraints. And then, of course, as I've been saying throughout the presentation, where we need to go is a place where analysis frameworks that are designed to be accessible and understandable to all stakeholders, not just the technical community, economists or the engineers, is deeply needed. I spent a lot of time during my career in Washington, D.C. presenting results from this type of analysis to other stakeholders, including a lot of policymakers and their staffs. And I realized that the task of creating clarity around how the problem is set up so that they can better understand what the important decisions are in the analysis was equally important to convincing them of the credibility of our particular results and our particular assumptions. And so I wanted to emphasize that here simply because I hope that some of the people who are attending the seminar who are in their academic careers might be interested in pursuing this a little more. I think that's something that would be very, very valuable. And I think, okay, so let me just summarize briefly and I'll stop. I think that this decision-making process that influences what the generation portfolio is going to be in the future is right now mainly a cost-driven, predominantly a cost-driven decision, although these other dimensions are recognized qualitatively. And there are some conflicting priorities amongst the different stakeholders. So I think our job from a research community standpoint is trying to figure out a way to enable a more intelligent decision-making process or inform a process better that can lead to a more sustainable generation portfolio over a longer period of time. We need this framework. I've already talked about that in quite a bit. And I can't emphasize enough, the most important part of energy economic modeling, as I've described it here, is not that it predicts anything. I mean, these models have so many assumptions, you cannot take the results and say they will predict. What you can simply do is understand sensitivities, and you can bring this observability and rigor to the key assumptions and key areas that will have the greatest impact so that the other stakeholders can recognize that. And then, useful debate can be held over where to go in each of those areas. So, okay, a lot of content. I'd like to stop here and maybe we can entertain some questions.
Oh, thank you, Revis. Again, as is the nature of these seminars, I first want to ask the students in the audience to articulate their questions. There's two ways you can do it: unmute yourself and ask that question, or get into the chat box and write down your question there. And Susan or I will kind of moderate that. I think Susan's been doing this quite well. And then once the students are exhausted with their questions, then we'll move on to the general audience. So students, go for it. Questions. Remember, there's no bad question, there's no good question, there's a question. Go ahead and ask it.
Yeah, I used a lot of terminology that, I know that despite my efforts to define things, I'm sure I failed to do that in some cases. So please, I encourage anyone to asked me to define, whatever it is, unit commitment or some of these dispatch issues or transmission questions or whatever, I'm pleased to try and do that.
So while we're waiting,
I have a question about, with like natural gas becoming more and more of an important power source, would you consider it more flexible than like existing like coal and oil plants?
Actually, I shouldn't answer so quickly, be so glib. A natural gas turbine, not a combined cycle, natural gas combined cycle, but a natural gas turbine definitely is the most flexible asset. And that's a big reason why they're out there. And I think we will always have, unless we find another asset that has that kind of same flexibility, we're going to always have some degree of those assets out there because they are the quickest. I mean, there's a term that they use a lot in power, they call turn down. The term turn down simply means, you can twist the dial to go from 100% down to whatever level you want. You can do that pretty fast. The gas turbines do the best job of that. The natural gas combined cycles can do that to some degree, but unfortunately, when you do it too much with the natural gas combined cycles, and there's a lot of those out there, that's an important issue because, go on a side tangent to understand the difference between the two. The natural gas combined cycles are probably growing more. More of those are getting built, or there's more interest in those than there are on the gas turbines because they obviously produce two forms of energy, and not electricity, and they produce basically thermal energy, and they can be very economically efficient. So that's attractive, and they are kind of better at being a baseload asset, an asset that runs steadily rather than just fluctuates. So those are very desirable characteristics in many ways. However, the trade-off is that the exhaust gases from the turbine part of the natural gas combined cycle are used to transfer heat to working fluid, water, usually making steam, and that heat exchanger, the heat recovery steam generator, doesn't like thermal transients created by turning up and down the gas turbine part, and so you get damage and cracking in the tubing of the heat recovery steam generator if you flex the output of the natural gas turbine part of the unit too much. Historically, those heat recovery steam generators, or HRSGs, HRSGs, were not built with the idea people were gonna go in and try to repair cracks and replace tubes and maintain them. They were kind of built as a black box that you just use until it was done. Now, of course, for many years now, people recognize there's an incentive to create more maintainable HRSGs. But that's an aspect of why those particular group of natural gas assets, natural gas combined cycles, maybe have a little bit less flexibility and have some other issues as opposed to just the pure natural gas turbines.
questions from students? Use your audio, unmute yourself, or enter it into the chat box. So while we're waiting for a question in the chat box, Ravis, did the 2015 study, which made Texas look very red, was it a kind of a forecast of what was to happen later on, a few years later?
It would be convenient to say yes, but no, I don't think you can accurately say that. I think that first, let me just emphasize again, I don't want to take your question's opportunity. These types of analyses, although it's the liabilities analyses, full disclosure, what makes these analyses useful is also a weakness. Because they're detailed, because they provide this observability on all these assumptions, and then you have these really interesting and complicated outputs where you can compare different questions. It's a natural tendency, particularly in the non-technical community, to view these analyses as predictive. They have done a really great job modeling, and they are predicting that in 2025 this will happen in this region, and they're not. They're definitely there's too much. Every one of these, many of the assumptions in these analyses has an uncertainty band around it, and so when you combine all of that, you just can't take these results and say they're predictions. So that is a liabilities analysis. So in the case of Texas, the reason for the red in that chart of the United States was because the level of increased operational flexibility needed for the generation assets in Texas was particularly high because of the fact that Texas had less interconnection with other parts of the country. So the operational flexibility demand that was modeled in this study was a result of increased deployment of renewable energy around the country. Now, Texas has seen, in fact, since the study was done, a substantial increase in renewable deployment. And so one could argue that maybe some of Texas' challenges were a result of that. I would probably make that argument for some reasons. However, obviously, some very important weather events happened that affected dispatchable assets like the natural gas combined cycle units in Texas as well. So some of the problems Texas has had in recent years can't be attributed exclusively to the predictions of this model related to increased renewable deployments and therefore increased flexibility requirements in Texas. The weather events that happened were a big factor, and of course, the model can't predict the weather. So I think it's somewhat fortuitous that Texas was highlighted in this analysis, and then we've had these, very newsworthy events in Texas. It's not entirely related.
So I'll read off a question in the chat box from a former student, so he qualifies. Policy is always changing. How do you find satisfaction in running multiple scenarios for situations that may never be? And somewhat tied to that, how do you affect policy to actually change based on these analyses?
Okay, that's a great question. I really appreciate that question. The first is, the first part of the question I think has to do with timing. Policies are changing and you're doing these analyses, and how can you really have an impact when there's this maybe a mismatch in timing? The second part of the question, which I'll come to, is how do you really go about influencing policy given this type of work? So let me answer the first part, the timing part. That's always going to be a problem. I mean, first of all, the policy world is fluid. And as we all know, there are an awful lot of reasons why policymakers do things that have nothing to do with technical insights to the power sector. There are economic reasons, purely political reasons, a lot of other agreements that are made, to get one outcome in another legislative domain. They make an agreement here, energy policy or something. So there's a lot of factors. I spent 11 years in Washington, D.C. working for EPRI, and so I had a little exposure to that world for a while. And one thing I learned was that while many of us in the energy sector bemoan the fact that there isn't some comprehensive energy policy that should be developed that the nation can use to guide and inform decisions, I think there's a strong political incentive not to have that, because historically, the energy world has many opportunities for politicians to do things which are beneficial to their particular constituencies. And so I believe, from my perspective, they enjoy keeping optionality open by not having too many constraints created by an overarching policy. So that is a problem for this type of work. Okay, and I think all you can really do is try to be adept at monitoring the policy world, anticipating where the dialogue is going, and try to do analyses that get ahead of where the policy is going rather than react. You have to be proactive and somewhat anticipatory. And that goes to my point earlier about this is why the technical community has to have an avenue to connect and have visibility and at least be aware of what's going on in the policy community and the economic world, the investment world. Now, that kind of ties, answering that, how do you do that, kind of ties to the second part of the question. I think, there are a lot of levels of doing that. I would first say, which is probably the reason I'm even working with Ramesh on these seminar series, I feel that more students and more researchers, I would think, if they were to choose this area and choose to make research in this area of how these things can be connected, maybe we come some ideas for ways to create more visibility in the stakeholder world outside of the technical community, mainly the policymakers, by producing results. The university community, even though those policymakers, and I can say this with absolute conviction from my time in Washington, even though the technical community, of course, that the political community recognizes that technical experts reside all over the place. They're in industry, in academia, in commercial companies, and so on. In practice, it seems to me that when Congress seeks advice from technical experts outside of their own organizations like the DOE, they go to the academic community first. That's where they go. They go to wherever, Lehigh or MIT or somebody, and they ask for prominent researchers in the academic community to provide insights. And that's why these blue ribbon committees that we see created mainly are dominated by academic people. Therefore, I think it's important for work on this area of how these things tie together to be done in the academic community, so there's a robust body of research to be drawn upon when the political community comes back to academia to ask questions. So that's that's one avenue by which I think more influence can be achieved in a productive way. Or I would say influence is maybe not the right word. I would say informing decision-making is probably a better way I like to phrase it. The second avenue, I think, just me personally, this is maybe a little biased, but I think organizations like EPRI are particularly valuable because they aren't commercial organizations trying to make products or services. They're not really political organizations advocating for a particular political objective. They're simply organizations which exist in this kind of this interface between the technical community and the other stakeholders by producing, relatively unbiased research that is made available to the stakeholders. And I think working with organizations like EPRI or creating groups that have that mission is the way to achieve that. If you go to Washington, there are many think tanks and groups which are focused on economic policy, and there are any number of think tanks that are focused on that, and they act as informers of the political community. Comparatively, there's not so many on the in this area of energy policy. There aren't that many groups that do that. Some groups will pick it up as a part of their portfolio, but not many are focused on it. So that would be creation of such groups would be valuable.
Okay. There was a third part to that question, and Nicholas asked, now that engineers need to talk to policymakers and those who want to get into that realm, be able to communicate like you did for many years, what skill sets do you recommend that they?
Okay, yes, that great question, excellent question, and yeah, I'd be happy to talk to people about this offline or down the road too, because I now I'll say I fell into this a little bit. I'm a nuclear engineer and an electrical engineer at the beginning, and it was evolutionary rather than planned. But I would say, obviously, obviously communications, all the skills that go with that are important. And I would say as an engineer, thinking to yourself, anything I'm doing in my technical activities, what would I do if I had to communicate this to an audience who's skeptical and critical? Not a technical audience, but another audience. Like if you were to go to your town, a good way to imagine yourself standing in front of the city council or some state group, and you're going to explain your work and why it's important and what impact it has and why would it matter to them. That situation is you want to develop capabilities to function well in that situation. I think it's important, therefore, to develop the ability to, I was going to say teach, but what I kind of mean by that is something specific. As I said earlier, I realized when I first was in Washington, the first 3 years I was there, I felt that my primary goal was to communicate some of the research that we were doing at EPRI. And I felt that the biggest litmus test was to convince people of the credibility of our research. We had the right type of people, we asked the right questions, we were using the right tools, the way the work was done was credible. And I realized in the first few years that wasn't really, obviously credibility is a prerequisite, but that wasn't really the central thing. The central thing was creating a description of the problem we were researching in a way that, say, the chief of staff or a senator could understand why we had chosen that problem and why these were the moving parts were most important. Empowering people to understand problems at that level creates a sort of partnership when you engage in communication with them about that problem. They have their own thoughts and questions about assumptions or inputs or why are we looking at this versus that? And when you create dialogue at that level, you're much more likely to get to a level where a decision comes out of it, as opposed to simply speaking in a purely persuasive manner. Washington is full of experts pelting senators and congressmen with expert opinions. What you need is a skill to bring people into the room with you about how the problem is formed and why you formed it the way you did, and therefore why your team looked at the problem this way and made these assumptions. And then you proactively engage on the inputs as well as the outputs. So skills that allow you to do that, focusing on resources, educational resources that let you get better at doing that would be extremely valuable. Not to mention, I think it'll make you pretty successful in your career from just purely a business standpoint.
And with all this money that is coming in with this version of this Build Back Better plan, I think there's a bigger need to have that language barrier between policymakers and technologists.
Well, I know that this may sound to some of the students somewhat general, these descriptions I'm making about communication, but if you are able to come in there and sort of, like I said, bring people into the room with what you're doing and how you're approaching it, not just what your results and conclusions are, you're going to sound different to the other 99 experts that are coming in there telling them what they should be thinking.
Question, another question from the chat box. Where do you see energy storage? Where do you see energy storage role in the discussion and way forward?
Okay, so that's an excellent question. And some of you who were at the October seminar might remember, I listed that as kind of one of the game changers that could shift the balance of some of the sort of basic assumptions that go into this kind of work. Okay, first of all, the two facets of that question. The first is, energy storage technologies, what they are, what's being done, who's working on what. That's not my area of expertise, so I don't know I can speak comprehensively on that. I know that a tremendous amount of energy is being devoted to finding ways to improve battery technology. That seems to me to be the primary avenue that people are spending time on. Batteries that are made out of less exotic materials, batteries that are more recyclable, obviously cheaper, batteries that can be cycled more times and don't lose their storage capacity. All those basic things are a big part of that. But the thing I would say, maybe from a systemic perspective, if we are able to create a storage resource that is sizable, that means you can store the output of a wind farm for on an ongoing basis, so large amounts of energy, dispatchable very rapidly. In other words, within a matter of minutes, the energy from in that storage facility can be discharged into this network. If those things could be achieved and be achieved in a way that can be done on a repetitive basis, and if storage facilities, because the cost could be lower to where you could have storage facilities with every renewable asset out there. So if that were to happen, you would be able to decouple the demand for electricity from the generation of electricity. See, the fundamental problem we have in our system now is that we are a real-time, on-demand system. When somebody flips a light on, output has to go up somewhere by a little bit, and what we would love, what would create tremendous capabilities in terms of both cost, maintainability, and lifetime of assets, as well as reliability, would be the ability to let demand change whenever it wants, and the production of electricity through the generation sites would be independent of that. Would be able to, you could produce energy when it's most optimal for the asset, regardless of when it's needed. So that would be a profound game changer if that could be achieved. So from a standpoint, is that a research area that's worthy of attention? Without doubt. A lot of players are in that area, but that would be a major change.
Okay. Question from Hal. Can the models handle the policy requirement of net zero by 2050?
Yeah, they can. The models can model that. In fact, many of the models do that. Exactly. For example, some of you may remember there was a different proposal. Gosh, how many years ago was this now? But this was back around 2006 or 7. But there was at that point in time, there was an expectation, which never materialized, of a national CO2 policy. And I think there was an emissions intensity goal that was to be achieved by 2050. These models are very flexible in terms of establishing it. So you can model a net zero policy. The challenge is that when you model, like, say, a very aggressive goal, and you just let the model run, of course, unless you introduce constraints that relate to economics or technical characteristics or something, the model will produce and deploy assets in whatever combination is needed to achieve that goal at the lowest economic cost possible. The art is in how to figure out whether you've represented all the technical capabilities and limitations of the system, the technologies we have, and then see how well the model can reach net zero. And often what you will see, depending on the assumptions that you make, is that a policy goal can be made. It just becomes a matter of how expensive electricity becomes to do it.
Okay. Any questions from the audience? Audio? I still have some in the chat box, so I want to give you guys a chance. Okay, a question from David. Do distributed generation and demand response make dispatch more or less challenging? Does the N-1 concern you that?
Yeah. I'd say this is an area we started to touch. That analysis that I showed you from 2015, a follow-on to that project that was started, but I don't have in my mind exact results of that yet. But I remember this was a recognized problem, was what does increased distributed generation and increased, programs which influence how energy is consumed, whether you have people consume less or you incent somebody financially to reduce their energy consumption. Say Duke Energy will pay you a little bit to let them adjust your thermostat down by half a degree for a couple hours a day, those kinds of programs. Those programs, I would say, generally speaking, increase the need for more operational flexibility. And the reason for that is that a lot of how those resources perform are customer determined. Distributed generation often is controlled or partially controlled by a customer who owns it. The programs which incent users to use energy in a different way or pattern, usually those programs are optional. The user can choose to do something based on an incentive or whatever, or choose not to. So from a systemic perspective, that creates some variability in what impact those resources will have. Therefore, that translates then to some added variability for the assets being dispatched on the system. If output is increased from those resources, the output from the dispatchable assets, the central station assets, will go down. If those resources are effectively generating less, then output will have to go up. So I would say it increases variability, and definitely it was recognized that we need to explore what the impact in more detail is of changing proportions of those kinds of resources. I'm using that term resource to cover those programs as well as the distributed generation.
Okay. Another interesting question here. Storage can relieve transmission congestion and reduce requirements to expand. Was storage considered in the analysis you showed that included with and without transmission expansion?
Yes. So the short answer to that question is a significant amount of storage was not considered, because at the time that study was done, the cost of storage on a large enough scale to have an impact on interregional transmission was pretty high enough that it didn't seem we were going to get meaningful results out of the model if we were to include that option. However, the ability to include storage and represent it at different cost levels. In fact, I think one of the recommendations out of that study was to do a parametric study of what if storage were available on those large scales at different cost levels, how much would that impact the results? So that was a follow-on recommendation to that study to look at that parametrically. And then of course, naturally, if let's say you got an output that said, well, storage at this cost level or lower would really change, say, for example, the need for interregional transmission, that would in some sense follow on with the question, well, can we achieve that? How achievable is that level of cost? So that's something we didn't model in that study, but it is something that these types of energy modeling tools can look at.
Okay. Another question here. Can you comment on the future of nuclear energy to address climate change, given the recent statement by 3 former regulators in US, Germany, and France stating that nuclear energy plays no conceivable role?
I've learned in my Washington experience that policy is highly fluid. I mean, things that look like they're cast in stone and are immutable can change in comparatively short time. In political space, a 3 or 4 year period of time is a very long time. So, I would have to say objectively, there's a lot of resistance to relying on nuclear power to address climate change around the world. I think, in my opinion, I think the reason for that resistance is not entirely due to reluctance on the part of policymakers. It's partly pragmatically due to the fact that there's such a large capital outlay necessary to build a nuclear power plant. I will not go off on a tangent on this now, but I think you could probably, given the cost of climate change, some of the consequences, you could probably make an economic argument for building nuclear power plants anyway from that standpoint. And I think in the long run, I can't see an option that we have to reduce the carbon intensity of the electric sector that we know how to do outside of nuclear on a large scale. I don't see it. You know, the other answer would be if we did address the storage question we were discussing earlier, and we, you know, had a very, very cost-effective large scale storage, we could expand renewables a lot more, armed with that storage capability, and maybe we could bypass reliance on nuclear if we were able to do that. So that would be an avenue. Then you get into the realm of policymaking and handicapping risks. Generally speaking, I would say it seems to me that a strategy that entails reliance on more than one direction is probably prudent, considering complexity and technology and economics that arises. So I would probably think that nuclear would be a part of the strategy, as well as pursuing storage development. But my answer to the question basically is I think there's a lot of reluctance to rely on nuclear now, yes, but I think pragmatic reality is likely to intrude as the climate situation worsens, and unless we have another development from another domain, I don't see many other options we have.
Yeah. Just one kind of overarching question, that slide on the mosaics, which showed variation from one region to another, that itself could occupy an entire semester of
Yes.
But every corner over time, you're seeing flexibility playing a huge role. And there may be different reasons in Texas, different reasons for California. Are there one or two overarching reasons, Revis? I mean, is it customer behavior be a big part of that? Or
you mean for why this flexibility surfaces? Yeah. I would say, no, I wouldn't say it's customer behavior. I would say the primary reason is simply that the introduction of I say renewables because they're the primary non-dispatchable assets have been introduced. There are a few other minor things like distributed generation and customer programs to change energy use patterns. That's another area where those are essentially resources which aren't dispatchable in the sense that you can't control them in a holistic, singular way like you can a nuclear power plant or a natural gas combined cycle. So, but the primary players to me are the introduction of wind and solar, and many states and nationally we have various mandates which at some level require the use of generation for those assets. And so what in practical terms happens to meet those requirements in different jurisdictions, you actually have to change the output level of other assets. So basically situations at a given time of day in a given week of the year, say in the Northeast, if in New York, let's say, if there's a mandate and I think there are mandates there to use, say, a certain amount of renewables, and energy usage is, say, lower than the normal peak at that time of year. So it happens to be a little bit of that particular week and that particular year, the energy consumption is less than typically at that particular time. Then you're going to have to turn down output from other assets. And the frequency with which those situations are arising seems to be increasing. And I can tell you that even independent of this analysis that I showed you, there's a whole other research community that's just focused on existing power plants and operational experience and how do we maintain them better and lower the cost of maintenance. Ramesh, you're very familiar with that. Mm-hmm. And that group of researchers has been seeing for some years now this increased flexible operations and seeing cost issues arising and reliability issues arising. So that the leading indicators of that were already on the horizon even before this kind of analysis was done.
Okay, is there any more questions that you would like to ask Revis? We're almost out of time. Any pressing question that you have Revis will be back 4 weeks from now, February 28th, to continue with part 2. And in between, the students and I will be going on a field trip to a distributed energy lab operated by PP&L, which is our local utility. So any last question before we close? Well, thank you, Revis. Really engaging, and as usual, there's so many things that you covered. But But we will, as I said, Revis will be back 4 weeks from now and covering other aspects that we alluded to in today's presentation. I'd like to thank all of you for attending, the students for asking those questions and others. And thank you, Shreya and Ashok, for your testimonial for Janak Raj. And hopefully his message will permeate in the lectures that you hear in the semester. Thanks a lot, everybody.